And welcome back. So what we're going to be looking at here are, once again, forces acting on systems, okay? So connected objects, objects that are connected rigidly, so they're not with springs or anything that can stretch or compress. But last time when we looked at this, we only looked at horizontal motion. We said, a camper is hooked up to a trailer hitch and they're driving down the road left and right. We've looked at boxes pushing on each other left and right. But what happens if we take something that's moving left and right and we combine it with vertical motion? We talked about vertical motions with elevators or objects moving up and down. We've seen a bunch of problems with this now. How can we combine these items together? And the way we can do this is with a pulley. A pulley is really just like a little wheel that's allowed to spin. And here's our pulley in a little picture here. But this pulley really just allows something like a rope that passes over it to change direction. It allows the rope to say, hey, instead of moving to the right, I want you to move up or down, or just any direction that we kind of set up with the pulley. We are going to use ideal pulleys here, so we are going to pretend for right now that there's no friction in the pulley, because friction is bleh. And we're also going to pretend that our pulleys are massless. Now, at the moment, you're just like, okay, I guess. But, as we do more physics later in the year, there is a reason why these are massless pulleys. It takes energy to spin a pulley, but we're not going to worry about it for now, okay? So in our little demo here, we have a block of cheese, and yes, it is blue. That is blue cheese, my favorite type of cheese. This cheese has been cleverly strung up with a piece of string that is wrapped over a pulley by a very clever mouse. I don't know who let this mouse in the house, but this clever mouse is trying to pull the cheese off this frictionless table. Now, if we kind of think about this, since this table is frictionless, any amount of force applied to the cheese block will cause it to move. That's a really weird idea. It's so weird that if you imagine for a second that, and this is going to hurt, but I nail your feet to the ground, okay? Like I nail you in. You could, if the rest of the world was frictionless, you could move any object. You could move a 10,000 pound block of steel just by pushing it. If you were nailed in and the ground was frictionless. Because as long as there's no friction, you know that F equals ma. And if there's no friction, the only force being applied is like your push, even if it's like 1 Newton. And even if that mass is 100,000 kilograms, well, if you take 1 divided by 100,000, you're still going to get a number. It's going to be small, but you are still going to have an acceleration. That giant block of steel is still going to move forward. It's just going to do so slowly, okay? It's going to accelerate at a slow rate. So it's important to think about that. We can pretty much move anything if there's no friction. In fact, you can move anything if there's no friction. It's just that acceleration may be very, very low, okay? So be aware of that. A lot of people are trying to get the idea that, hey, if something's really heavy, you just can't move it. No, you can, as long as there's no friction. We have that misconception because here on Earth we're stuck with friction for everything, and that's a true statement if there is friction, but if there's not, you'll always be able to move something. So in this case, even if this block of cheese was the size of Mount Everest, this mouse could still pull it off the table because this table is frictionless, okay? Now, when this block begins to move, the block is going to move over this way, and the rat is going to move down. And this is going to cause something a little weird to happen here. So let's take it to the lab and see just what's going on. Okay, so let's take it here. So here's our lab setup, and we can see on the table that what we have is one of our motion carts. Okay, so right here is one of our motion carts. It's the blue block of cheese, ta-da. And over here, let's just pull out a little bit of cheese, or a little bit of rat. So here is a small rat. Here's just our 20-gram mass. It's nothing crazy. It's not going to whip this cart around. But attached to the cart is a little bit of string. And then we've actually seen this demo before, how this cart is going to accelerate. We know the cart's going to accelerate once the mouse starts to pull down on it. But to get an idea of this, let's think about what's happening here. When this cart begins to accelerate and speed up in that direction, not only is the cart accelerating this way, but the mouse is accelerating downward. And since these objects are rigidly connected, we know that both of these accelerations, they have to be the same. Whatever the mouse is accelerating downward, the cart is accelerating to the side because they are connected. So this is actually a very similar idea as to you just pulling the cart sideways. So what would this look like if we actually drew this with a free body diagram and we actually put this into a kind of an equational setup? So because we know block of cheese is accelerating, in our case here, like to the right, and the mouse is accelerating down, but these accelerations are the acceleration of the system. They are the same, okay? So what we are going to think about here is the direction of the acceleration we are going to call the positive direction. In fact, we could call it the negative direction, but the key thing to recognize is that this pulley is causing this entire system to accelerate like this on this kind of curve. Okay, that's our acceleration. Now, sometimes in physics, you'll hear this called a U curve. This isn't so much a U in this case. We'll see that in the next problem. With the pulley systems. But basically what we're doing here is we're saying, look, if we're moving with the acceleration over and then down, let's call that our positive direction. And let's say moving against that acceleration is the negative direction. Well, what this means is that if we look up top, if we take a look up top for the block here, what we're saying is that up top, going to the right is positive and the left is negative. For the rat's case, moving up and down, what we're saying is that moving down is positive and moving up is negative. That's our U setup there for each of our things, for the cheese and for our little mouse rat thing. Andy Dwyer, mouse rat. Okay? So that's our kind of setup we have here in terms of just positive and negative directions. And that's arguably the most important thing to think about in a problem like this, because the free body diagrams are going to be very simple for us as we've got experience with them now to set this up. So let's actually crush through this problem. We've got the block of cheese and it's on the table, so let's draw that block of cheese. And it's being pulled with a tension to the right. There's no force acting to the left because there's no friction here. And if we then look at the mouse, we'll put the mouse in red. Well, what forces are acting on the mouse? Well, the mouse has a weight, which is equal to mg, pulling down. And remember, this rope that's connecting them, it has a tension acting in both directions. That's Newton's third law, equal and opposite forces. So the mouse actually has a tension pulling back up on it. And remember, these tensions are equal. We also know, just like we pointed out moments ago, that for our mouse, down will be positive, up will be negative. For our cheese, the right will be positive, the left will be negative, because that's the direction of motion. That's our accelerating direction. And at this point in time, this is actually very, very similar. It's pretty much identical to the problem we did yesterday with the truck pulling the camper. Because if I took this mouse and I flipped it sideways, this would look very similar to saying, hey, the cheese is being pulled like this, and the mouse has a weight force now going sideways and a tension backwards. That is the exact same as our previous problems, except our mouse is moving up and down. So let's do what we've done before with problems like this and set up two F equals ma equations and see where we can go with that. So if we set up F equals ma for our block of cheese, our sum of the forces is equal to a mass multiplied by an acceleration. In this case, we only have one force. It's the tension. It's positive. And this is going to equal the mass of the cheese, which is 1.5 kilograms, multiplied by an acceleration of 3.3 meters per second squared. And look at that. We have just solved the tension for the string. Tension is going to equal the mass times the acceleration. 1.5 times 3.3 is going to equal 4.95 newtons. So kind of neat there. If we want to set up our second free body diagram, or F equals ma equation, so we loop around the rat itself. Okay, we see we have two forces there, so we better have two forces on our F equals ma equation. So if we write out, here's our F equals ma, since we have two forces here, tension and the weight, I better have two forces when I add them together. So when I do that, I'm going to have weight is positive, so weight minus the tension, because I'm adding a negative number, minus the tension equals the mass of the rat times the acceleration. Okay? And we know some of these values here. We know in this case what the tension is. We found that up top. So these tensions are the same. Let's bring it down and plug it in here. So we're going to have weight minus 4.95 equals the mass of the rat times the acceleration, which we know is still going to be positive 3.3 meters per second. We're saying that, look, the direction of the acceleration is positive. The acceleration is down for the rat, but we're calling down the negative direction. So that's a positive 3.3 meters per second squared. Okay? Now this gets a little bit tricky to solve for, because what we're trying to find is actually the mass of the rat. We're looking for mr. But I don't really have weight. Or do I? Recall that the weight of an object is equal to its mass multiplied by gravity. We actually put that in our free body diagram right here. So what we can do is let's substitute in the mass, whoa, that is a bad looking M, the mass of the rat times gravity, which we know is 9.8. Remember, that's going to be a positive 9.8 because we've called down positive. I like to always keep gravity as positive 9.8 and just let the direction for my forces dictate if that's going to be a positive or a negative number. So we've got M times G, so mass of the rat times 9.8 minus 4.9 equals mass of the rat times 3.3. Because mg and ma, those are both masses times accelerations. Those are going to be for us like terms. We can actually put them together. In doing so, I can subtract 9.8 mass of the rat to each side. So minus 9.8 mass of the rats. So 3.3 minus 9.8 is going to give me a value. So let's see, 3.3 minus 9.8 is going to give me negative 6.5. So I'm going to have negative 4.95, oops, there should be a 5 there, equals negative 6.5 mass of the rats. And at this point, if we're just looking for the mass of the rat, we can divide each side by negative 6.5. Negative 6.5 this is actually very nice because we see that the negatives divide out. Our mass can't be negative. If we had a negative mass, we knew we did the problem wrong. And what we simply find here is that the mass of the rat equals, let's see, 4.95 divided by 6.5. We get 0.76 kilograms. So what we quickly see there is with this, we have the mass of the rat now of 0.76 kilograms. And that's the whole problem. That's what we're kind of solving here for. It's very, very similar to what we did with the truck and the camper in previous things, except this time we just need to be careful about our acceleration is changing direction. So we just need to make sure our positive and negatives are properly aligned for whenever we set up our F equals ma. But this is finished.